Welcome to this online training about the high bandwidth memory found in Intel FPGA Stratix 10 MX devices. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. In this training, you will learn about high bandwidth memory, or HBM, a next-generation high-speed memory technology built directly into Intel Stratix 10 MX FPGA devices using System-in-Package, or SIP, technologies. You'll see why this integration offers a very compelling solution for many of today's most demanding applications. You'll learn about the features of the hardened HBM controller found in Intel Stratix 10 MX devices and how to parameterize and integrate the controller into an Intel Quartus Prime project. Finally, you'll learn about HBM controller efficiency and how to optimize and measure the efficiency of your own HBM interface design. Here is the agenda for this training. This first part of the training is an introduction to the HBM standard, including a look at its unique features and its architectural design. In subsequent parts of the training, you'll learn about the features of the hardened HBM controller, or HBMC, the user interface required from your design to communicate with the controller, how to implement the interface in the Intel Quartus Prime software, and how to measure and optimize the performance and efficiency of the interface. Let's get started with an introduction to high bandwidth memory. The ability to access and use large amounts of memory has become a key bottleneck in many current applications. Data center, high-performance computing systems, and other industries and applications require access to as much memory as possible as quickly as possible. However, as the requirements for memory bandwidth have increased, many of the options for implementing this memory are not able to keep up with the requirements. Let's look at the challenges in trying to meet these requirements. First is the current projected roadmap for the most common type of memory, DDR. DDR memory bandwidth has scaled pretty well over the past decade, with an approximate doubling of bandwidth for each generation. But moving to a DDR5 with a projected bandwidth of only 40 gigabytes per second, or a future standard beyond that, is not enough to keep up with the demand. Next, the available memory bandwidth is limited by I/O. It's not possible to create a memory interface with enough I/O pins that is wide enough to meet demand. Adding more components is not a solution because that just increases power and board size and layout requirements. Power is the third challenge. System power budgets in most cases must remain flat or even be reduced. With the amount of long parallel board traces and buffers required to drive those traces at high speeds, as well as the additional memory devices that would be required, the power consumption of the memory could quickly outweigh the entire system's budget. The final challenge is the integration of memory directly into a computing device. While FPGA devices do include memory blocks, these blocks are highly specialized and do not provide enough memory for the applications mentioned. While standard higher capacity memory technologies could be integrated directly into the FPGA, there are limits to what can be included. Clearly, new innovations and technologies are needed to meet the requirements of today's applications and industries. So what new innovations are available to help meet these needs? Moving beyond legacy DDR memory, the industry is moving to a number of competing standards for 3D stacked memory. Stacked memory is appealing because it provides large capacity in a small form factor. The standards for 3D stacked memories can be divided into two groups. Serial interface memory, such as Micron's hybrid memory cube and the MOSIS bandwidth engine, use high-speed transceivers and fewer signals, allowing them to still be used as external components. Parallel interface memory standards, such as high bandwidth memory and wide I/O memory, still use wide buses for high bandwidth, so they are usually integrated directly into the computing device to avoid the issues involved with long board traces. To get a better understanding of these new memory technologies, let's look at the ones currently supported by Intel FPGA. Hybrid Memory Cube, or HMC, is a serial interface stacked memory that uses through-silicon vias, or TSV, for connecting up the layers of the stack. It offers up to 320 gigabytes per second bandwidth, with each serial interface providing up to 30 gigabits per second. The stack is made up of discrete memory cores with dedicated memory controller die at the base. Most HMC devices include 4 serial links that can have either 8 or 16 transceiver lanes. So a full-width mode device has a total of 64 transceiver lanes. HMC is a separate device on the board, so it requires its own power and termination, making it a higher power option for external memory. HMC is currently supported by Intel FPGA Aria 10 and Stratix 10 devices. See the online training linked here to learn more about HMC. High Bandwidth Memory, or HBM, is currently in its second generation as a JEDEC standard. Like HMC, HBM2 uses TSV for connecting up the layers of the stack. An HBM2 stack can provide up to 256 gigabytes per second bandwidth and run with clock speeds up to 1 gigahertz. Like external DDR, it uses a wide parallel interface of 1024 bits, where each I/O provides up to 2 gigabits per second. Unlike HMC's built-in controller, the controller for HBM2 is implemented in the host device. Because of the large number of parallel signals required, HBM2 is implemented in an integrated device that includes the memory controller. For Intel Stratix 10 MX devices, HBM2 is implemented on the main device die using System-in-Package, or SiP, technology. Here you can see how HBM2 compares to other DRAM solutions. LPDDR has good power efficiency, but tends to have less available bandwidth than other solutions. Standard DDR memory provides a good balance between power usage and bandwidth. Looking at the next generation options supported by Intel FPGA, both HMC and HBM2 provide high bandwidth, but HBM2 is the winner when it comes to low power. Let's compare traditional external discrete memory devices with HBM2 implemented as SIP. With a traditional DRAM implementation, the FPGA connects to the external DRAM through traces across the PCB. HBM2 has a small footprint and low power requirements compared to traditional DRAMs, so it can be coupled to the host die, eliminating the need for external board traces and termination. You can see on the right how the HBM2 DRAM is located within the package and interfaces to the FPGA through an on-die interconnect bridge called the Embedded Multi-Die Interface Bridge, or EMIB for short. As already noted, HBM2 can support large bandwidths up to 256 gigabytes per second and can operate up to 1 gigahertz, making it the clear choice for meeting the memory bandwidth requirements for all next-generation applications. Now let's look at the basic HBM2 architecture and how it is implemented in Intel Stratix 10 MX devices. As already mentioned, HBM2 is three-dimensional DRAM technology consisting of a stack of silicon dies. The top die consists of the main stack of DRAM, while the base die includes the I/O connections to the host device. The top die includes either 4 or 8 individual DRAM dies that are connected together using TSVs. The 4-high version has 4 GB of capacity, while the 8-high version is 8 GB. Each die in the stack consists of 2 physical channels. These channels are duplicated in the 8-high stack. In the 4-high stack, each channel is 4 gigabits, or 512 megabytes. Because each channel is duplicated in the 8-high stack, each one provides 8 gigabits, or 1 gigabyte of memory storage. Each of the 8 physical channels can be controlled and managed independently from all the others using completely separate I/O connections through the base die. Each physical channel is divided up into 2 pseudo-channels. Pseudo-channels differentiate HBM2 from the original HBM specification by breaking up the 128-bit I/O interface to each channel into 2 groups of 64 bits. As such, the maximum bandwidth with an 8-high HBM2 stack is 256 gigabytes per second. Here is a block diagram of an Intel Stratix 10 MX device. HBM2 is integrated into Intel FPGA Stratix 10 MX devices using SIP technology. Devices include either 1 or 2 HBM2 stacks at the top and bottom of the package, and each stack is either 4-high or 8-high. Each HBM2 connected to an EMIB interface has a dedicated hard controller that can be customized for each physical channel. The controllers are connected to a Universal Interface Bus, or UIB, to access the EMIB to the memory. The HBM2 SIP consists of the components listed here. We'll take a look at these components on the next few slides. Besides the HBM2 memory stack itself, the SIP consists of the UIBSS and the EMIB. It also includes the user logic interface to the HBM2 controller, or HBMC, which makes use of an ARM AMBA 4 AXI interface. A buffering adapter for this interface can be added in if necessary. So, as noted, the HBM2 itself is organized in stacks and is supported in 2 configurations, either a 4-high stack consisting of 4 DRAM dies or an 8-high stack of 8 DRAM dies, plus a base die. Here is another look at a 4-high stack. Each DRAM die has a density of 8 gigabits and consists of 2 channels. Looking at the channels in a little bit more detail, each one consists of 128 data I/O signals and its own address and command bus, making each channel completely independent of all other channels. Each channel also has access to an independent set of memory banks as shown in the image. This means that banks tied to channel 0 cannot be accessed from channel 1, for example, and the same rule applies to pseudo-channel 0 and pseudo-channel 1. Memory density is dependent on the stack height, so channels in a 4-high stack each have a 4 gigabit density, while each channel in an 8-high stack has an 8 gigabit density. Here is another view of a 4-high stack. It consists of the base die, the 4 DRAM dies, and the 8 channels with the 128 DQ, as mentioned earlier. It is important to note that when the stack height increases to 8, there are still only 8 channels. Moving to an 8-high stack, you can see that with 8 DRAM dies, even though technically each die contains 2 channels as shown, you still access only 8 logical channels. The memory density increases because each of the 8 channels is now essentially duplicated. Along with the increased stack height, a 1-bit stack ID signal is introduced in order to distinguish between the upper and lower 4 dies. After the HBM memory itself, the UIB subsystem consists of the components that allow the user logic to communicate with the memory. First is the UIB PHY. The PHY includes the UIB physical layer and the I/O connections to the memory. The UIB PHY drives the signals over the EMIB to perform the basic memory access operations. On the other side of the UIBSS are the rate matching FIFOs. These are used to handle the clock crossing between the user clock domain and the PHY clock domain. We'll look at the clocking options for these two domains later. The final part of the UIBSS is the HBM2 controller, or HBMC. We'll be looking at the HBMC in much more detail in a moment, but the HBMC is what performs all the read and write data transactions requested by the user logic. It also performs memory access optimizations and housekeeping to make sure that data is transferred and stored in memory correctly. As mentioned, the user logic interfaces with the HBMC through an ARM AMBA4 AXI interface. When connecting to the HBMC, you have the option of adding a soft logic adapter that can gate the ARM AMBA4 AXI interface valid signals. Recall that the valid signals in the address read, address write, and write data channels are sent from the source, the user logic, to validate the information sent. The HBMC must respond with the corresponding ready signals to complete the handshaking before a transaction can begin. The adapter can gate these signals with the ready signals if the user logic is not always ready to receive data from the HBMC. The adapter also stores the write response and read data signals coming from the HBMC when the user logic is not asserting the associated ready signals. If the user logic is always ready to receive data from the memory, the adapter is not required. The final part of the connection to the HBM is the hard HBM2 controller, or HBMC. This hardened controller offers higher performance, higher efficiency, and lower power usage than a controller implemented using FPGA fabric resources. We'll discuss controller efficiency in more detail later. The HBMC contains independent controllers for each of the 8 physical channels. However, 2 ARM AMBA4 AXI interfaces per channel provide user access to each of the pseudo channels. As mentioned earlier, pseudo channel access was added to the second version of the HBM JEDEC specification. The HBMC only supports the pseudo channel mode of accessing the HBM2 device. Each controller consists of the read and write data paths and control logic required for translating user commands to the HBM2 stack, allowing for both 32 and 64-byte access to the memory. An additional sideband ARM AMBA APB interface allows for additional user requests to the HBM2, such as user-controlled refresh. Here is a more detailed look at pseudo-channel memory access. Pseudo-channel mode is new to HBM2 and basically splits a channel into 2 pseudo-channels. In normal operation for the original HBM specification, which is referred to as legacy mode, a channel is treated as containing 128 data bits. With pseudo-channel mode, the channel is split into 2 64-bit pseudo-channels that share a common address and command bus, but allow for separate decoding and execution of commands. This separation helps maximize the throughput of the memory. This timing diagram for legacy mode helps show the advantage of pseudo-channel mode. The TFAW timing specification of the memory restricts the number of active banks to 4 within the specified time. Due to this restriction, in legacy mode, there can be 4 activate commands, but then about 7 cycles of accesses are lost. Note that this mode is not supported by the HBMC. With pseudo-channel mode, there are no idle cycles within the TFAW window. This is because the 4 active window restriction applies per pseudo-channel, effectively maximizing throughput and allowing more flexibility when accessing HBM2. In the timing diagram shown here, activate commands alternate between the two pseudo-channels PC0 and PC1, avoiding the legacy mode's TFAW penalty. HBM2 memory access signaling can be compared to traditional DDR memory signaling. Here is a comparison of the address and command signaling. For DDR4, the address and command bus runs at single data rate, while the data bus is what runs at double data rate. The DDR4 signals consist of an address bus of up to 18 bits, a 2-bit bank group and 2-bit bank address, 1 bit for command and address parity, and a 1-bit activate signal. Looking at HBM2, unlike DDR4, the address and command bus actually runs at double data rate. The signaling is simpler as well. It consists of a 6-bit row and 8-bit column address, essentially splitting the DDR4 address bus into two separate signals for HBM2. There is also a 4-bit parity signal and a 1-bit address error signal that is used to notify the controller that an error has occurred on either the row or column address signals. Taking a look at the data signals, the DDR4 data strobe is bidirectional and is designed so that there is one DQS pair for each 8 DQ. There are also data mask or data bus inversion signals for each group of 8 DQ, plus the 72-bit DQ bus itself. For HBM2, notice that the data strobes are unidirectional and consist of separate read and write DQS signals. Another key difference is that instead of having one DQS for each 8 DQ as in DDR4, HBM2 contains one RDQS and one WDQS for each group of 32 DQ in the 128-bit wide data bus. HBM2 does include DM and DBI signals for each 8 DQ, similar to DDR4, but adds a 4-bit data error signal. Each of the 4 bits corresponds to 32 data bits and indicates to the controller when a data error occurs. With HBM2, you don't need to worry about setup and hold timing, since it is guaranteed within the package. All memory access commands require only 1 clock cycle, except for row activate commands which require 2. In the timing diagram, you can see that the activate command takes 2 clock cycles, while the read, write, and precharge commands take only 1 cycle. Here's a comparison between DDR4 and HBM2 read timing. The double data rate read command is issued, followed by a fixed read latency, before data becomes available on the DQ lines. And here is a comparison of write timing. Again, the write command is issued, followed by write latency cycles before the data is written to memory. HBM2 supports ECC, which is also supported in DDR4. However, HBM2 ECC cannot be enabled when DM is enabled, since the ECC signaling is shared with the DM signal. HBM2 also supports 2 additional unique features, temperature reporting and implicit precharge. HBM2 includes 2 temperature reporting features, temperature compensated refresh and the catastrophic temperature sensor. Temperature compensated refresh is performed by monitoring a 3-bit temp signal from the memory. The temp signal reports the required refresh rate for the hottest device in the memory stack. The refresh rate is determined by the vendor. This helps to maximize throughput and avoid excess junction temperatures by issuing refreshes only when needed. The other temperature reporting feature is CAT trip, or the catastrophic temperature sensor. This sensor is responsible for detecting if the junction temperature of any die in the stack exceeds the CAT temp threshold, which is programmed by the manufacturer. If the CAT trip signal is enabled, the controller must stop all traffic to the memory and stall to avoid potentially catastrophic damage to the part. The device must be powered off and cooled down to clear the cat trip signal. The final HBM2 feature is implicit precharge. With implicit precharge, an activate command can be issued within the same bank without explicitly issuing a precharge command first, as would normally be required. This saves the controller from having to issue the extra precharge command, reducing some overhead, but the precharge timings still apply as shown in the diagram. This concludes part 1 of the training. If you'd like to continue the training, you can register for parts 2 and 3 for free at the links shown here. To learn about additional resources available to help you with using HBM2 memory in Intel Stratix 10 MX devices, continue to the next slide. For more information about HBM2 in Intel Stratix 10 MX devices, see the online resources listed here. The IP parameter editor includes basic documentation on all parameter settings, but the HBM2 IP user guide goes into greater detail on those settings, as well as detailed looks at IP signaling, clocking, and simulation. The device overview helps you to understand all the features that are available in Intel Stratix 10 MX devices, including HBM2. The listed white papers describe the technologies that make HBM2 integration possible and the advantages you get with HBM2 as a system memory solution. Finally, the ARM AMBA4 AXI specification describes in detail the standard interface required for accessing the HBM2 stack. Intel offers many options for FPGA training. Our instructor-led training classes are full-day classes taught by experienced training engineers, either in a public class, on-site, or through a virtual classroom. We also feature almost 300 free online training classes, just like this one, that allow you to study a topic at your own pace. All of these classes can be viewed on a computer, and most of them can also be viewed on your favorite portable device. You can also visit the Intel FPGA YouTube channel to watch all types of instructional videos, from short how-to videos in our Engineer to Engineer playlist to detailed webcasts on many different topics. See the Intel FPGA training website to learn about our recommended curriculum for every type of user and to register for a class. For further information about using the Intel Quartus Prime software, be sure to check out the online help, as well as the Intel Quartus Prime Handbook. There, you'll find detailed information and multiple examples to help you use all of the features of the Intel Quartus Prime software effectively. Be sure to check out the Intel FPGA website at www.altera.com to find solutions to the most common technical questions and problems, view design examples, and download product literature. For local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. Check out the Intel FPGA Wiki for up-to-date articles written by Intel FPGA engineers. Finally, the online Intel FPGA forums are a great place to connect with other users to share experiences and find solutions to common issues. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this online training about the HBM2 memory found in Intel Stratix 10 MX devices.